So our next speaker is Edgar David De Leon Zeppi, and his presentation is titled "SCRIM Friction Testing in the USA." And as you all know, safety is becoming a issue of bigger importance in what we do in pavements and surfacing treatments. And there's performance measures coming which we're going to be using on a day-to-day basis. We use skid testing in Montana. We don't do as much as we'd hope. Resources are a little bit strapped, but just a few weeks ago I was looking at the skid numbers on chip seals versus unsealed 3/8 inch plant mix. So I'm interested to hear more about this. Dr. De Leon has worked in the area of pavement management, and transportation engineering for over 30 years. He is currently a research scientist at the Virginia Tech Transportation Institute, working for the Pavement Surface Properties Consortium and the National Sustainable Pavements Consortiums, and other multidisciplinary research projects that addressed end result and performance-oriented specifications. So, welcome, Edgar.
Thank you. Thank you very much for inviting me. I have to thank specifically David Luer for providing me this opportunity, but this is something that is really going to be taking off, I think, in the very near future because of what Darren was saying, because of the crashes. And unfortunately, those are the bad news. I think these are part of the good news. The outline of my presentation, and I'm going to try to go very fast because I have a lot of slides, but I'm hoping I can finish. I'm going to go directly into answering your question, what is the SCRIM? Then I'm going to give you a little background on why we're doing this, and a couple of slides just to refresh the memory or present some of the concepts of friction that a lot of people might not know. And then into the concept of pavement friction management, and specifically the crash data analysis, which a lot of us have never done, even though we collect friction. And then a couple of case studies and some of the results of or examples that we have gotten with this device, and some final considerations. So to dive right into the topic, what does SCRIM mean? It's a ideway-Force coefficient routine investigation machine. This is a device that was developed in England by TRL, and the current device that we have is collecting friction, macrotexture, and with the aid of an inertial measurement unit and GPS, we can also get grade, cross slope, and curvature at the same time we're getting the friction. We also have a front video, and we're being able to do this with every tank of water for 150 gallons, 150 miles, I'm sorry, of continuous data. Regardless of what some people might say, this is an American truck. It was built in the Volvo North American plant, which is just about 10 miles from Virginia Tech. Builds all the trucks, Volvo trucks for North America. That includes Canada and Mexico. And the reason why we did that, there's two reasons. One is we didn't want to deal with the 24 volts that they use in Europe. And the most problematic one is, don't ask me why, but the EU standards and the EPA standards are not the same for the diesel, even though they probably use the same diesel, but it's just probably some protection device or something. This is the heart of the unit. As you can see, it's measuring friction dynamically. That means that at the same time that it's getting a horizontal measurement, it's also getting a dynamic measurement because it's got two transducers. The angle of the tire is 20 degrees to make it possible to measure a 34% slip. I'll explain that a little bit later. We can operate between 15 and 55 miles an hour, and it also has a Macrotexture laser right in front of the tire so that we don't mess it up with the water. And we all know why we're doing this, all the federal rulemaking and everything, because there's going to be a report that is going to include fatalities and serious injuries and the rate of fatalities and serious injuries. So what has been a steady decline in fatalities is just gone up. According to NHTSA, just this Thursday, they announced that as of 2016, analyzing the trend of the first half of the year, fatalities are up 10%. So that's going to be a big thing, because that 10% of fatalities is not going to be enough to overcome the slight growth of 3% in the vehicle miles. And so that rate of fatalities is actually going to increase the rate to about 12% from 11.2 that we have right now. Now, most of us in this room are pavement engineers, and we have been exposed to these three words for most of our career. We have to build pavements that are safe, durable, and economic. And so I'm going to come back to this, but we've all heard this, and I just want to pinpoint that the first word there is safe. That has probably not been the case in all of the disciplines that deal with pavements. Another thing that I want to point out is that for every fatality, there's about 55 injury crashes, about 120 just property damage only, which makes a total of about 175 crashes. So if you know your total fatalities in your state, you could probably just multiply that. I did that for Virginia, and it came out to be a pretty good number. I'm hoping they put this presentation on the website afterwards, but if not, I can give you all a copy if you need this. So when these fatalities were happening last year, and after the tallying came up, and that was last year, the actual number of fatalities from 2014 to 2015 had gone up 7%. And just articles like this started coming up, and I'm not being a native English speaker, but what is complacency? So are we satisfied with how things are, and we don't want to make them better? So it's a very insulting article for us, I guess, and for everybody. It came out in Forbes on July 7. And then on July 6, July 6, the Center for Disease Control, and don't ask me why they're doing this, they came up, I guess because now fatalities were one of the 10 most serious killers in the United States, but they come up with things like, oh yeah, we could reduce by half these fatalities because they've been proving strategies in other parts of the world that can do this, and they come up with statistics like this. So we know that among all of the, let's say, richest countries, we have a very bad record. Now they're doing it the wrong way. They're comparing it with dividing them by population and not by vehicle miles driven, but still, we don't have a very good record, and that's something that we have to address. Two of the major killers in the United States are, you can guess it, alcohol, 31%, and speed, 29%. So just right there, you have 60% of the causes of the crashes. Now, yeah, if you can reduce that, then you can get rid of all those fatalities, but it's not easy. And then the other problem, use of seatbelts. And that one is, for me, is really hard to understand, because I don't think anybody here drives without a seatbelt, and I don't know anybody that drives without a seatbelt, but yet there's about 10,000 people that are dying every day because of the lack of seatbelt. So if you can explain that to me, it'd be good. So according to the CDC, we have these problems, and the recommendation are use the seatbelts, don't drink and drive, don't drive over the limit of the speed. And one that I added is probably going to be causing all these increases that we've seen in the previous years, is the texting and probably cell phones. But that hasn't been proven yet. So my question to you is, what can we do as pavement engineers? Now, we can't solve 100% of the fatalities and all of those things. And so to declare that we're going to have a zero vision and we're going to do it all, I don't think that's possible. But we can definitely help. How much? I think we can help 10%. That's a ballpark figure. But I think it's going to have to be a effort that is going to take more collaboration, communication between different entities in each DOT. Why? Because a lot of you guys here are maintenance engineers, and you're in charge of the treatments on the roads. So we can increase the friction of the roads by putting right treatments, by doing the correct analysis. That's going to be subject to, the pressure that is going to come, and believe me, it's going to come, because the compounded increase in fatalities, if you take the 7.5 and then the 10, is about 20%. So we can also determine where these friction improvements are, and that's probably the job of the safety engineers. And so that's why I'm saying this is going to be has to be concerted between all the parties. And then probably the materials engineers are going to determine how we're going to do it and when we need to do it to improve the friction. Because everybody here agrees that probably the only thing we as pavement engineers can do to reduce crashes is to improve the friction. And when we don't have friction, we all know what happens, because there's nothing more terrible than driving down the road, applying your brakes, and your car doesn't stop. I don't know of any other thing that we can do to stop crashes as pavement engineers, but we're going to have to work with these other groups. This is the friction curve of how and why friction happens. It's just that the very left part of the curve, you have a tire that's free rolling right about here. So the brakes are not being applied. As soon as you start applying the brakes, that friction starts going up, but it reaches a peak. That peak is known as the critical slip or the peak friction point in your curve. But after 15 to 20% of pressing that brake, your friction actually stops dropping. And then you can go all the way to the end where the previous devices used to lock the wheels. So you see you're not really using the best friction. This is the principle of ABS brakes. ABS brakes work around this peak. So when you apply ABS brakes, the brake is being applied, it reaches the peak, then it lets the tire off, it reduces the friction, applies it again, and this is all happening in microseconds. So knowing this, the other two bits of information that we need is this slide. If you don't know what microtexture or macrotexture is, this is a very simple explanation. The macrotexture, as Brian Schleppio from Ohio very correctly said, is just the channels of where the water is going to flow out of the path of the tire so that it gets away and we can start applying the brakes. The microtexture is the smaller channels of water that are in each individual particle, and when those disappear is what we call polishing of the aggregate. When that is not there, then we don't have any microtexture, and then the next slide explains why we need those three. The first part of that tire imprint is where the water is being evacuated by the macrotexture. The second one is where the water is being evacuated by the microtexture. And so after we remove the water, then the actual rubber is going to start breaking with the aggregate in the road. But if we're lacking the macrotexture, for example, then that part of the circle in the back, number 3, is going to be very small, and then we don't have enough friction to stop. But it's actually friction is a result of adding both microtexture and macrotexture. So microtexture is very related to your aggregates. If you have very good aggregates that don't polish, you probably have very good microtexture. Macrotexture is just how you're building your pavement so that the water can be evacuated by the pavement itself. And somebody talked about grooving before. Oh, Kelvin. And that's macrotexture in concrete pavements. In asphalt pavements, you can see it right there. It's just the spaces between the individual aggregates and the bottom of the binder. Very dense mixes do not have very good macrotexture, and that's what makes them dangerous. And I'll show you some examples. A couple of other examples is we also need, on curves specifically, we need what is called super elevation or cross slope to be able to make the turns. If you don't have the cross slope, then what happens is what is depicted here at the bottom drawing, you're probably gonna fly off. And the equation is there. What has not been explained is this equation is really, once you break it up, it's a function of both the friction and the cross slope. So why are, for example, high friction surfaces working so well on curves? Because you don't have the super elevation, but you do have an increase in friction. Those two elements working together are fighting the vehicle from leaving the road at very high speeds or at very small curves. Another thing that happens when you don't have good cross slope is you can have water ponding, and then you can have hydroplaning. So just showing you what the tire looks like for the friction. What you're trying to get is a coefficient of friction, and whether you're testing micro or macrotexture. In the case of the SCRIM, the tire is so thin, even though it's 3 inches wide, but you're actually getting a very slow speed of friction because of that 34%. So let's say you're going 50 miles an hour, you're testing at 17 miles an hour. So you're testing actually in the range of the microtexture part. With the log wheels, they do it actually, you're actually being capable of doing it in both ways. If you use the tire all the way to the left, what is called the rib tire, then you can use it to determine the microtexture frictional part of your pavement testing. If you're using what is called the smooth tire, which is the other one in the middle, and similar to the ones used by the runway friction testers and the grip tester, which are the smaller tires, you're mostly testing your macrotexture. So the project that we have, why we brought the SCRIM to the United States, is called the Acceptance Testing and Demonstration of a Continuous Friction Measurement Equipment. And basically, it's a safety project because we want to reduce highway crashes and related fatalities, but evaluating the recommendations of the AASHTO Friction Guide. So our mission is to go to 4 states and develop pavement friction management programs, which I'm going to explain, by using friction, texture, crashes, and other data that I explained before. So we get texture, crashes, and everything, and we establish friction demand categories. Friction demand categories are just, as I'm going to explain, why we shouldn't be using the same friction number for all sections of the pavement. So in the first part of this project, these are the states where we went. These are the miles that we got of continuous friction measurement of all those elements of data that I talked to. And recently, North Carolina has joined us, and we went down in August and measured about 500 miles. And we're going to be comparing the numbers with the grip tester and with their log wheel skid units, which use a rib tire. So just want to show you some of the results that we got in one state, and I sanitized some of this data so you don't know what route it was. But the relationship between the black dots, which are the log wheel skid test results, and the blue dots, which we're getting this is actually a summary of the information every 10th of a mile, whereas the state was testing every mile. It's pretty consistent. It's pretty on top of it. So we're very happy of the results. And also you can see that every mile is not capturing all of the low points that we are able to capture. With the SCRIM, we're actually being able to collect raw data every 4 inches. Then you can see it every meter, and then you can actually average it every 10 meters. And then we're getting a 3 minimum point average, moving average, every 1/10 of a mile, just to characterize. And we're aware that the PMS data sets are in every 0.1 of a mile. That's why we are averaging the data every 0.1 of a mile. And the crashes are also assigned every 0.1 of a mile.
What's the y-axis on that? Can you explain the y-axis?
Oh, I'm sorry, that's just the friction coefficient for the SCRIM. They're both put in 0 to 100, being the friction coefficient 0 to 1, but multiplying by 100.
And the minimum number that is acceptable is?
It depends, like they said yesterday, where you are, what tire you're using. So I'll get into a couple of examples of that. Yeah. This is concrete pavements, by the way. These were asphalt pavements. These are concrete pavements, and the little black dots, or white dots, I don't know how you want to call them, they're the skid test results, and the red ones are the ones with the SCRIM. They also follow the same pattern. These are on some bituminous surface treatments. We were not able to test many of those miles, but the trend is still significant. One of the problems that we have is when we compare measurements, a lot of people are just making simple correlations. This Excel allows you to do this in about 3 seconds, I think, if you have 2 columns of X and Y data. The problem being is you're assigning the error to whatever is on Y and fitting everything to X. So maybe one of the ways we need to do this is with what is called an orthogonal regression, which sets the error among the line and not assigning it. Regression is very good when you're growing beans and you want to know how many pounds of fertilizer you want to increase to get a certain yield. But when you have 2 independent measurements, and if you remember, they always talk about the dependent variable and the independent variable. Well, when you have two units that have their own error, you cannot use simple correlation. And I just wanted to explain that with this. These are some of the correlations that we have found with both the blue dots in concrete and the red ones in asphalt. But we're taking it a little bit further, and in order to not us answer this question, we went to TTI. You know, there's 2 calibration centers for the lock wheel skid testers in the United States. One of them is in TTI, the other one is in Ohio, in Columbus. And we were there in September when we were doing our measurements. So we did measurements with the lock wheel skid tester from Texas and what they call the area reference measurement system, which half of the states that calibrate their units calibrate against that. Dr. Wambold and Don Zimmer. They have a lot of different surfaces that we tested on. They have different textures. So we're expecting to have a very good report and a very good relationship between these 2 units. So then we'll be able to compare that y-axis better. So the question is, and that's why I was talking about the friction demand categories, do we need the friction to be the same everywhere? For example, in Virginia, we have that magic number that is 20, and we're testing with a smooth tire. Is that enough? I found a study that in Minnesota, they actually have it in 3 categories as what should be the minimum, but it's still around a 30 with a rib tire. The problem is this section the same as this, or is this, or is this, or is this, or is this? You get the point. We should not be thinking of the same friction everywhere because we do not need the same friction everywhere. So in the UK, they came up with a scale depending on the types of segments of roads where you have, oh, I'm sorry, this is UK English, or you're not going to understand it, so I'm going to translate. This is American English, so motorways are really interstate pavements and so on. But you see there's a increase depending on what type of category of pavement section it is. The highest one being probably the crossings for pedestrians, and the lowest ones being for tangents in interstate pavements. So we're also doing that. But the most important part of collecting friction data is matching it with the crashes. And unfortunately, that miscommunication that I said existed between the groups before has not allowed that to happen. So the safety guys have come up with these maybe wonderful equations, regression equations on how to predict crashes, which we're also doing with condition of the pavement and everything else, which are called safety performance functions. And we pretty much use their methodology, but they don't understand squat about friction. So it's very hard for us to go and explain that to them, but it's going to have to be done. So that's what they use. And finally, we have a model for crash prediction based on what happens if we increase the friction in this point. We put it in the regression equation again. It's not so simple. You have to do some weighing in and all that. But it's possible now to predict what is that increase in friction going to allow you depending on the treatment that you're doing and how many crashes are being reduced. The idea being you're going to increase the friction where the benefit cost ratio is going to be allowing you to do it. We don't want to increase the friction just because it came below a certain threshold. It's because by increasing that friction, you're going to be able to reduce the number of crashes, and then economically, it's possible for you to defend the fact of doing that treatment. And that's what I was talking about, that we need to do. We've gotten a lot of input from the safety folks, and they say, well, what you should be using is something called a crash modification factor that does before and after studies. But that's like saying on Monday morning, yeah, I can tell you what all the scores were from football on Sunday. We're actually on Friday, and we're trying to predict those scores. So again, the result was the economic analysis. For every 0.1 of a mile with improving friction and or macrotexture, because that's one of the things that was very interesting to find out. So now I'm going to go into the case studies. I have about 4, I think. But this was one of the state routes that we measured. And I'm going to show you one specific point. What this has allowed us, though, has been a network level analysis, but I have to show you individual cases, but they pretty much resemble this. So these are about 27 miles of continuous measurement. The yellow dots are the individual lock wheels. Now, we asked the operator of the lock wheel to do every mile for about 10 miles. So you can see in those 10 miles, the pattern, again, is very, very effective, very similar. The measurements in the bottom are the macrotexture measurements. And if you can see the axis on the right, those are millimeters. The macrotexture is actually very good. It's about 1 millimeter. The little dots are just the 1/10 of a mile average that we are assigning to those continuous measurements. However, in the other part of the project, when he's only doing 1 mile measurements in the lock wheel, if you can see there almost at the end, the last 1/10 of a mile, which is the 59.9, there's a big drop in the friction of the continuous measurement. And the macrotexture is still good, but what is that big drop at the end of the continuous measurement? Well, it's this intersection where everybody's turning off to the right, so they're braking, and then when you turn off to the right, it just showed up in the analysis as one of the best parts that this is going to show. If you increase the friction there, you're not going to have as many crashes. Why? Because then those rear-ending crashes are probably not going to happen. Obviously, it wouldn't hurt to have good signs and everything else. It just happens to be also on a curve. And with that exit, it just makes it much more harder. Case 2 was a real eye-opener. One of the states that we went to, which measures with a rib tire, so they're measuring microtexture, and the SCRIM is also measuring microtexture, had very good friction numbers according to the microtexture. However, when we include the macrotexture, it's below 0.5 of a millimeter. And some points there's like 0.3. That's a very smooth surface that reflects the very good dense mix that they have, which probably gives them a lot of durability and not a lot of oxidation, but it's actually causing all of those crashes. Now, you notice that spot there in the middle that has a very high macrotexture, and it has a little bit less of the microtexture, which is reflected in the friction. So what happened there? Looking at the video data, they had a change in pavement. So most of the pavement is new pavement. All of that red 0.4 millimeter, it's a very dense mix. And that last part is just old pavement that, of course, as it gets cracked and everything, it has more macrotexture. The next to last case is we did some measurements in Virginia. We had a call from one of the districts saying there had been a fatality and that the local fire chief had said that it was because there was no friction on the road. So we went there. It starts in this, it's a downhill slope, and as you move forward, you see there's a ramp where the traffic exits. And then, but right at the end of that ramp, there's a left-hand turn. So we measured the friction was fine. We measured the macrotexture, and it was also fine. That's the red and the blue line. We measured the grade, and you can see it's going down, and then at the bottom of that curve, it actually pulls up, so it's kind of like in a vertical curve sag. But then we looked at the curvature and the cross slope. And if you look a little bit closer as you're getting close to where the ramp is, but you're still in the curve. That's probably the place where your curve is probably having to be super elevated, but it's not, because you have that ramp, and if you would put the super elevation, cars trying to get on the ramp would have a big jump to get there. And that's shown here. So that's what the cross slope should be. And so, unfortunately, that fatality is still there. The last case is just to show some of the capabilities of the equipment and the data collection. You can actually see all of the data you collect on Google Earth. So this is one run that we did specifically to measure a high friction surface on a curve that is right there. So that's the whole survey. The yellow point, the yellow dot or pin just shows the location of the truck at that time. So this is the beginning of the curve. You can see the change in the material. This is the end of the curve, change of material again. And these are the results. It was interesting, and I'll show you why later. You have these peaks in Macrotexture, even though your friction is the same. This, of course, is the high friction surface, and then this is the end of the pavement. So you have a pavement that has a friction of about 50 before. The high friction surface is about 65, I think, and then you leave, and the friction drops to about 40. And I actually averaged, so it's 46, 67, and then afterwards it's like 33. And your Macrotexture line is in the bottom. And so what were those peaks in the Macrotexture? Well, they were actually those lines where they had actually grounded out the temporary markings. So just some of the final considerations that I have, and I'll be finished in about 2 minutes. 49 of the 50 states use the lock wheel. I should make a parenthesis there, because one of the states that uses this lock wheel is actually using a new lock wheel, which is actually getting data in smaller intervals. But it still has some of the limitations in curves. If you ever go in a curve and you test one of these things, if it's a very sharp curve, it'll just go away. People don't test in curves. Most states measure between every half a mile or every mile. We saw what happens. We miss data. Macrotexture is possible, but it's not common. And then the crash data analysis needs that friction data at least every 0.1 of a mile. So I have included a report that we made for Virginia using another continuous friction measurement equipment, but it has the same type of analysis and actually has this analysis. You're using about 2 gallons of water at 40 miles an hour. If you increase the friction, that amount of water is probably going to go up. So if you were to measure every 0.1 of a mile with the normal tank that comes with these units, you could get about 150 tests. If you do it every 0.1 of a mile, you're getting 15 miles. And then you have to go out for water again. And that becomes very, very, very bored, very fast. If you would use a 1,000 gallon tank, which you can use 500 tests, you test 50 miles. 1,000 gallon tank is probably not gonna happen for a lot of states. So in summary, with the E274, you can do about 50 miles a day with the SCRIM with 2 tanks, and that's 4 tanks of the E274, 2 tanks of the SCRIM. That's your productivity. Now those miles a year, those are really 60,000 miles of what they're doing right now if they're measuring every mile, or 30,000 miles a year if you're doing it every half a mile. I made costs of that, and the direct cost is almost 1/2 of what it would be to do that. So with that, I finish my presentations. I would like to make a few pages of acknowledgement to the Federal Highway team, my team back home, and some of the consultants that are also working on this, and the states that are participating in this project, the people that have been so gracious to accept us. And in every state, we have also met with the safety folks and the materials folks, because this is a project that's trying to do this from the beginning. And the TTI, of course, for the testing. These are some pictures of when that truck was being certified in England. in England, as you can see from these pictures, they have 17 trucks and their network has 10,000 miles. So if that's any, that's the white one there is the one that TRL owns. With that, I'm open for questions. Thank you.
Well, let's